Okay, so we'll wait for anyone joining online, and then we'll start a little bit late, but we'll start. Okay, so we'll start in a second. We still have few English-speaking students, so we'll keep continuing in English. Well, yeah, will help people in the like person. So those who come to the classrooms, that's advantage. Then we can go and try to help to fix code and understand things. So, but before that, so start with with this home task. Go do the code review. As I see, actually, that's not too bad. We have quite a lot of submissions, but only not all of them have nice pictures with them. That's kind of interesting. When you submit the, especially for the next tasks, when you submit some of the works at home, be nice to have screenshots with some visualizations also of the results, you know, like how well these models work, rather than just having the some loss plot or something like that. But okay, it was not specific about that. But good news that there is at least seems significant amount of works finished. Okay, let's share the screen. So let's do. So last week, the skip connections, the way to do. So last week we talked about the way so that you have deep neural network, then calculate partial derivative down to the input layer. It becomes 0. If it add the plus, it becomes something that that brings the error down to the even to the first block, first function. So now let's look at this step by step at the. So I gave you some interesting architecture to try out. By the way, today's session is about unsupervised learning. Actually, it's not mentioned up there, but the unsupervised learning is basically learning models without labels at all. So, and this is the very basis of language models. All of the large language models have two phases. We will look at them when we talk about transformers. But first phase 1, unlabeled data training. So just like take the common crawl corpus, books, whatever, and then the second phase is making them to behave like chat, basically. So, and this is based on reinforcement learning mostly. So, yeah. So this was the task. Inception, a net model. There's many different models you could try out, and the schema which we try to do is something like this. We'll look at how people manage to do this a little bit. Any questions, write in the chat as well, or we will discuss in person. Just a second, full screen, sketch. Okay, I have sketch. Okay, full screen. Cool. Yeah, you might think about the architectures. Which architectures are like commonly the best? I think last time we looked at that there is these benchmarks on ImageNet, and from the architectures, only the vision transformers and efficient nets are kind of on the top mainly. But the other architectures are. So we'll never know. Maybe next year will be something different. So we still need to know how to build them. So. Okay, so right, I don't have. That is interesting. I assume that if I press double click, then the image is also open. Right, the images are not open of the loss functions, but let's look at the code. Okay, so this is the inception block of one student. So the convolution, sequential, yeah, so this is also a common practice where you can build multiple sequential models and then combine them together. So this is something I asked you specifically, please not to do, probably because this code is generated, but basically, so we talked about this. So in Python, this looks like a function call, and why actually this is the case. So basically the module here also, if I can override operator call like this, and then I can do actually, so okay, let's turn off this for a moment. So and if I do anything with this, I can even operate. So do you know about operator overriding? No. So no, in the programming languages, no. Okay, so this is good if you could tell me what you know and what not. So then, so these operators, this is something useful to know in general in programming. So let's say this will be some kind of new object, for example, inception block something. So this will not be functioning code, but just for understanding. So with these double lines, these are operators, and this is the same also in Java, C++, C#, any programming language, and this is actually related to this line. So if I do here like dummy inception block, and then if I do here another one, so this will be dummy 1, dummy 2, then first of all, if I call like this dummy like a function, it will execute this part, okay? And if I do something like dummy 1 equals dummy plus dummy 2, it will execute this part by giving in the other the dummy 2. See? So, and this is actually a kind of fundamental thing to understand. Did you know about operator overriding before? Yeah, okay. So, but this is a fundamental in the sense that if we are talking now that PyTorch and NumPy allows us to do mathematics in this way, so imagine like if I have these vector operations and NumPy vector operations, they do like they're just NumPy objects, and somebody implemented that there is an add to understand how this works. So that's just under the hood how all of this works, and then this is also just for the clarity of the code. You always try to write code in a way that the other person who looks at the code understands as soon as possible what's happening there. Now this looks as a function call, and the best way how to write these things is actually self dot branch something forward forward and then the x. So even though it works like that, this is much more cleaner. So that's one. Oh, there's even more strange things happening. Definitely looks like generated code. So again, for your own sake, try not to generate code, doesn't help. So the relu here, I think I also, when I write code with you, I don't do this. So why do you think relu should not be in the constructor? Do you have any ideas so far? Like, yeah. Yeah, so remember that all of these torch and end modules, the one reason why we actually have them, and this comes back to the very beginning, if I press dummy parameters, remember this function? So this function collects learnable parameters, right? And how it works, it goes through my member variables and looks if something is learnable, right? So if I would add here, oh, by the way, there is even more strange things happening. Wait, so maybe this is not generated code, because I think that if I would generate it, it will not give such strange thing. So if I would do relu here, then it's okay, because this is my whole structure, right? And this, there is a learnable convolution and so on. But to do this here, this is like it kind of tells you that you don't understand fully what you're doing, because basically this is there's just a function, everything below 0 becomes 0, and everything else is the same. So there's nothing learnable there. So, and normally how people write this is they just write here torch relu like this, and this is the same. So you don't define it as a attribute, and this kind of, you might think this is trivial, but from the sense that you understand what you're doing, it kind of shows you that you understand where is the parameters and where is the functions. So that's one. The other kind of, so let's do step by step, but it's actually, so now I'm convinced that this is not fully generated code, so thank you for that. So we have something to talk about. So here, the other thing here, this is also fundamental. So the, okay, so we could have, remember we have these heads at the end. So do we have head? We don't have head here, but we have head somewhere here probably. FC, so we have FC here, great. So we have FC here, that is good. So okay, so what we can do right here is consequential like this, and add linear one do this, right? And do any of you know like why this doesn't make sense, or you would like to sort of explain? Because this is wrong, completely wrong, basically. You know idea, yeah. So, but if you have tell, so it, you know, like not like too many wrong answers, just so we can learn. So okay, so this is something to challenge, to think about. But basically, what happens here is following. So this is actually not difficult to understand. So you have x and y. So I will project from x to y, and so the linear is, remember, is rotation times bias, rotation plus bias. So if I have some kind of inputs coming in here, 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 and then I have first projection. So, and this projection moves these guys basically to the blue ones here, right? So basically, you understand, right? It's nothing complicated here, right? So, but this is the first linear layer, and then I will add these. So basically, what happens? These now are y, right? So we move these guys from here back down now to maybe some other position, right? As an input, and then comes the next linear layer. Actually, maybe I can use some colors different. So the next linear layer projects down to there. But the trick is that I could just use so I even don't need the previous orange one. I could just use the last. So the last linear layer which I will apply will determine my output. All of the previous linear layers will just so it doesn't matter like how many linear layers I put. The last projection is my projection that I will get. All the previous projections are just linear projections. They don't change any. So it doesn't pull out anything. It doesn't move it around in non-linear manner. So this doesn't make sense to add many linear layers without non-linearities or some other functions in between. And here we see that case, like convolution. And this is interesting to think why exactly this happened. Maybe this is my fault. Yeah, I did not specifically said that there should be ReLUs between, but this is the case. Like we could actually look at this more. I'm a little bit now not fully convinced what's happening here. So let's see. So inception net implementation GitHub. Kind of like I would say like 99% that there should be ReLUs in between. I think also in Torch Vision they have implementation. So inception net conv block. So this is not convolution. That's a conv block. Where is the conv block? Okay, here. So this conv block. Yeah. So there is a ReLU. So here is the convolution batch norm, and then the F ReLU. So it's not based inside. So this is the case. So yeah, and even batch norms in front. But yeah, I don't blame you too much, because it seems that I in my scheme I did not. So I have ReLU here, right? But I don't have ReLU up there. So this is definitely my mistake as well. So yeah, so there should be also ReLUs. Okay, let's look more. So then the concatenation. Concatenation also important to follow what is concatenated with what. So dimension 0 is batch. We've never concatenate batch. For the features, so the 4 features, it goes like this. We have batch, channels, width, height, or usually other way around, height, width. And then in this case, the channels are concatenated. And then the output, right. Inception net here, max pool, block, dimension 1. Yeah, softmax also function that you don't need to learn softmax. Oh, and here we go. Yeah, this is interesting, but I mentioned you many times that you shouldn't do this. So, okay, loss function. That's why I encouraged you to write your own loss functions based on the equations, because you could fall in this trap exactly. So what is the trap here? So this is just the knowledge of the library. So you use softmax here, right? And you then use this torsion and cross entropy loss. I'm quite sure that this is very bad idea, so I can show you. So if you would write, remember logarithm, minus logarithm, so on, right? Easy stuff. But then if you use this, then you need a little bit to follow around with this. So it's not just that simple. So PyTorch, let's look documentation of this function. Cross entropy function documentation. I think it is here somewhere. Okay, I kind of remember that it was more complicated than a logarithm. Yeah, so great. So the function is this basically. Okay, maybe it's okay. Let's make a picture out of there. So this is that function actually. So as you can see, it is not really cross entropy. It is cross entropy plus the softmax inside. See? So what happens actually is that you call softmax twice. So, but it really is like that. I know many times, like where there's models that people don't follow this through and then have problem. By the way, you know why they do this? Because if I like some like years earlier, we actually in NumPy with hand did the derivatives of these things. I just at some point realized that it takes too long. But basically, if you do derivative separately from softmax and cross entropy, then it's more complicated. If you put it together, then it's much easier. So that's why they do it. Yeah, because logarithm and exponent together, this is very nicely derivable. But then if you have just exponents, then you have a Jacobian matrix. So this is here the situation. So again, from the perspective of making models, it's actually not that difficult. You just need to follow what you're doing. Like if you're using any kind of interesting functions, then definitely look at what is the equation before committing to it. Also, here is this term. This is also good. You remember? So okay, we can check this. Do you remember what is this? Weight in the front. What does do? What that does do? By n. So no, the bias would be if there is wx plus b. That is the bias. But what do you think in the loss function, if you remember? So here we have, yeah, unbalanced. Yes, true. That is super key. Like I think I recently had also one consultation with one company that builds image classification models, and they also didn't have anything like that inside. And then they have and the balancing is also really interesting. Like if you have, we will look at maybe it's next week even. I'm not sure. Maybe next week. So image segmentation models. Like we will look at these today with unsupervised autoencoders, variational autoencoders. So it means that you get an image, you get out an image, but imagine you get an image and you get out the masks, right? Like you do YOLO and whatever these. So, and then it depends. Like you have, for example, on the images you have dogs, cats, right? And the number, let's say there's 100 cats, 200 dogs. But then maybe dogs are twice as big as cats, and then if you work the loss function on pixels, then you need to calculate on the big pixel space, and then maybe you would like to have a random sampling algorithm that gives that the dogs and cats are about the same count, but it's corrected on the pixel scale here, the loss. So it is really interesting problem. So to just keep track of it. So okay, so that's that. I probably cannot see too much on these issues, but let's look at more examples. So here's another one. Another okay. This looks again. I would be time to say this is generated, okay, but maybe not. Um, so yeah. Okay, so this is again from the programming perspective. Kind of feels like this is not generated, but just because it's not consistent. But here, like I would advise you to always do programming like this and not like this, basically. So imagine, like, of course, maybe I know at this moment I know what means 16 and 24, but then if somebody else looks at my code, he don't know or she don't know the code. So it's always better to use either named parameters or named variables, basically. Like it's always you look at the code in the way that somebody else looks at it and reads it easily. That's something. It's very strange that everybody have this call function. This is a little bit telling that kind of what actually it means, that either it's generated or because normally everybody would write it like that. Okay. Right. I'll look at the chat also in a second, see if there's something interesting. Oh, here's something interesting. This is very interesting. Why would somebody do this? Let's see. This is very strange. So with torch no grad, that is something. Is it yours? Some of yours? No. Okay. So this basically means. So what actually this means? So with again there is operators. Enter operator, exit operator. So basically I can rewrite the same stuff here, like torch set grad enabled false and then true. So and what it does, it disables the automatic tracking of the pointers of which functions I called. And in this case I want to have, for example, feature. Right, so this seems like, okay, I understand what the person is doing here. So the person is trying to hack the situation so that don't need to calculate what will be the feature size here. Get flattened. Oh, this is crazy. This is basically nice. So one nice thing is that person understood that needs to call this thing so that it doesn't learn some. So if the person would not do this, then the model will start learn all of these things. But basically, we could just debug it and calculate the size, and then we don't need to do this every time. Or we can use the formulas which I gave you. So this is really strange implementation, but nice that it seems that somebody tried to do this themselves. So this is cool. This is cool. So let's see, but better not do this in production environments. Better just calculate your size or use like this adaptive average pooling. I think I showed you adaptive average pooling, right? Remember adaptive. So it means that here is the output size, should be called output size. Right, where is the name? See, output size, it must be output size. So it calculates the kernel, stride, and padding. It was maybe not the best way, but it will calculate so that the output is one by one. And then do you remember this or right? So if you have like a batch, so for example, if I had before a batch and then there is 2888, and then let's say the 10 by 10 small picture, then after this thing I will get 1 1 1, and then I can flatten it down easily. So it's really useful stuff. If somebody else missed this is very commonly used, in all sorts of models, not only these. Okay, cool. Okay, I already spent quite significant time. Let's move on to today's lecture. I probably will not be able to cover everything, even with this. So, okay. So this slide is actually from Jan LeCun. Do you know Jan LeCun? I think I've mentioned him. So he's from Meta AI director. He's the one who worked first on this MNIST dataset of the letters 90 to, I don't know, 4 or something, and they also 1999, I mean 1990, early 90s, very beginning, he worked on contrastive loss functions. So something that is very cool and used nowadays actually. And he did these things when everybody else did not use them. So by the way, nowadays he's a little bit I would say not crazy, but he is like some interesting ideas. So he's working on energy models. Energy models are actually really also kind of cool. So it means that they use backpropagation in inference, not in the training. So it's even crazier. Plus also these two, Geoffrey Hinton got also this Nobel Prize, and this is the same level guy. So and they both are kind of like when they publicly speak about AI, they say a little bit crazy things. So nowadays, but let's say those yeah. So about 30 years ago, they were pioneers basically. So and this is a slide from him, and this I agree. So he says that the machine, like all of these deep learning models, so they are like a cake basically. So we so far looked at supervised models. So these are models where I have data and label, and so this is like icing on the cake. But the most of the cake is the self-supervised, unsupervised models, where the idea is that like you just observe data and then you encapsulate data. Then afterwards you can build your supervised model on top of it. And this is actually the way how most of the models nowadays work. You can use unlabeled data to get higher accuracy using supervised, and then the reinforcement learning is this cherry on the top, which we will look also at the end of this course. This is like the ChatGPT is trained with reinforcement learning, but usually reinforcement learning is used for these like robotics applications and the computer games and stock tradings and anywhere where it's kind of like difficult to write the even the loss functions, even the labels. You have just like long sequence, signal, good, bad. Basically, that's that. So, okay, cool. So then let's jump into to actually how this works. Where's my notes? Okay. So we will build these initially these autoencoder models. Then they will become more and more complex, and these quanta variational. So what was the name? Quantized auto VQ vector quantized variational autoencoders. They are actually part of the state-of-the-art GANs and so on. So they're really good. So how this works is I have an image. I have the convolutional model, for example. It can be also a transformer model. Then I have this small vector representation, and then I reconstruct the image back. And basically, my loss function is either square error or mean error or absolute error. This is the reconstruction loss on this end from the same as an input. And the target is that I will get something in this Z space. And for that Z space, we can get really interesting things unsupervised in unsupervised manner. So I think maybe I have even more examples, and then we will build ones, and then we will have even better models very soon. So here's this encoder decoder. I need to also show you one more thing. So chicks. So and if you do it right, by the way, in the first go, I don't think we will get it so beautiful. It's actually not that beautiful, but basically, when you do it right, then all of the semantic features cluster together in the Z space, and it's actually really cool. So maybe I can show more examples. Do I have some better picture? Okay, I have better picture. So have you heard about the dimension reduction methods or not really? No? Okay, so this is something very powerful actually. Okay, I need to. It feels like we will not be able to cover everything today, but then we will maybe do 2 lectures with this maybe, or just give you some material so you can cover, because there's many things to cover. So imagine that this space, each sample is actually a picture of what we had in input. And when you train this model, if you do it right, it will, by the semantic meaning, place those samples, or this is like the z space of that vector. So this is two-dimensional reality. There are 128 dimensions in the way that if I sample here, it will generate 1. If I sample something by it, it's 7. So it's very smoothly going. And this is really, really powerful for many reasons. So before those reasons, I just want to show about that dimension reduction, because if you understand that in these models, in the middle part, this is not just two-dimensional, this is probably 256 dimensions, right? But how then we can display it nicely like this? So to do that, there is these couple of methods. Just a second. We'll find some material to show you. Right. Let me quickly give you that. Okay, so there is one small tool to do this. Maybe later I can run one of my own experiments as well. Oh man, why it's not loading? Simply refusing me to load stuff. Okay, not sure. Okay, well, while it's loading, I will just write down. So the tools, the methods, basically, you can get them in sklearn as well. So these are the dimension reduction methods, state of the art. So PCA, that is the linear. Then there's the principal component analysis, linear and kernel. Then the other one is popular to use is TSNE, and then another one is UMAP, and the old, but sometimes it's used also, this LDA. But these three top are really good. I'm not sure why. Okay, it's loaded. So let me show you some examples. So the data here is, for example, we have the cancer dataset, we have iris flowers dataset. I think we worked with that some time ago. So 4-dimensional parameters for iris shape of the leaves. Okay. So and then if I apply these dimension reduction methods, then from 4 dimensions I will get, for example, in this case, 2 dimensions. So each flower is the dot. And these dimensions, PCA1, PCA2, they are just abstract dimensions. Basically, they are not my feature dimensions. And here, this percentage by this dimension means how much variance that dimension describes. Actually, I can show you even more interesting way. Where is the picture like this? So normally they actually use kernel trick, but you can imagine that what it does is this. So you have projection, and this is actually helping us to understand also called linear projections for. So projection from 2D space into 1D space, right? And what we want to have is a projection where there is the most standard deviation between all of the samples. So it describes the best the space you're looking at. Like for example, now at this moment, this is bad projection. It's everything is just in the one block, and then when it's spread out, then it's good. And here it means 73% that it has like this 73% of the space of the samples are like a good projection basically, and here is 22%. So this is 3 times or maybe so 3 times less important dimension than the first dimension. But still, that's why also they look a little bit in that shape. But so what you can do with this, first of all, you can visualize the similarities between things. So you can calculate Euclidean distances between things. You can calculate the cosine distances between things. And this is something that you can use in, for example, research. Like if you have surveys, right? Surveys, and then you want to display your data. And you can do this in 2 dimensions, 3 dimensions, and so on. So that's what we're doing here with that high-dimensional vector. And now we get this. And why this is useful? So there's many things, but so one thing which is very commonly used with these unsupervised methods is like Apple Face ID, for example. So or ray identification systems. So you would train. So this is like ray identification system on people walking, but it can be faces. It can be, I know one company now building with the infrared camera these blood vessel recognition. So you train your model with these training set people. Then basically you deploy this system in real life. You film the environment. You detect the people. Let's say with YOLO detect the people, and then you have this query image. And this query image is never been in the training set, never in the training set. But then I can use the cosine distance between all of these samples, and all of the samples which are the closest or the threshold will be those samples. Imagine, so how cool is that? So you can like train a model that never seen classes and then use it in real life. So Apple Face ID like works like something like that, but they use a little bit more fancy these loss functions, but basically that's that. So that's one use case. Then what other use cases? The anomaly detection basically. It can be not only images, it can be also sensor data. So here's I think some kind of sensor data. So you trained your so this could be like water quality sensors, right? There comes the data, and then all of the training data was always in that area, and then suddenly some kind of strange event happens and the points start to fall in cluster in some other part. By the way, for the clustering, there is a really cool models available. Basically, I think in this course we focus on deep learning, but the older machine learning techniques for the clustering, they're all really great. There are some of these models are really powerful, and then you combine them with this. This is like you can do crazy things. Like for example, here. So these are some of these clustering models that you can methods. Have you heard about k-means? Do you know k-means, right? This is like really dumb method where, for example, you put randomly initially 3 cluster points, right? Then you find that all of the closest points are here, and then calculate the new cluster center point based here. So this will be my new, this will be my new, and repeat this method until everything is split. So this works great for these guys, right? Maybe even for this one, but it's not working great for example like that. And here it's actually really cool. Like the HDB scan optics and these kind of methods, they are density-based methods. That's why they don't work on this one, by the way. But they are able to detect, for example, this noise. They are able to automatically understand how many clusters are there, for example. So these are really imagine combining that with the previous. So you can do like really interesting models, applications, and so on. So that's why I really like actually these unsupervised models. So that is the ray identification, the anomalies, right? So these are some things which we can do. Then of course the generative models, right? Maybe I do have some example of generative models, because you can imagine you just take some kind of picture, right, and then play around a little bit with scroll bars, and then you have different picture, right? So this is early days generative models. Nowadays they are actually more complicated, but hopefully we'll get there. Okay, so the last piece of like the puzzle for actually building these things, because mean square error loss we know how to build, is how we can make this part. So basically, so this part, the decoder. So for decoder, actually what we do, we use the same convolutions as for the encoder. So here is, I think this is kind of nice illustration. So you can use the same convolution for making pictures larger. Just if you put there like these deletions, like the paddings in around everywhere. See, understand? Like if I just artificially put zeros around like some pattern, I can start making the convolutions larger, and they call these transposed convolutions. And here's also some of those equations. Not sure in my template, do I need equations? If I need, then there are. So you can calculate what will be the output of the transposed convolution. For the transposed convolutions, there are also some disadvantages. Maybe we will be able to talk about them. But this is the kind of the standard one way. Okay, so this is the same equation, right? Yeah, this is the same equation. Okay, let's leave it just that one. Okay, cool. Okay, let's build that. I will put in the and by the way, if your computer is a little bit laggy or something, then you can do this also on Google Colab at this moment. But it's better to do this on PyCharm or Visual Studio Code or something like that. Okay, Moodle. This will be a simple autoencoder, the vanilla one, the most simplest one, and then we will get to those more complex ones, which are actually much better. So interesting. So this I accidentally translated the wrong task, I think. Let's see. They had many lectures already, so it's a little bit. We'll get it. Just a second. Okay, implement encoder part, right? So so let's just call it implement encoder, implement decoder as well. I don't want to have two separate tasks for encoder and decoder. I know, I remember why I did this. So I think I mentioned you once this, especially you here. So the for this AI course, we in the spring we have like AI Olympics for the high schools and for first years bachelors, and then usually we get people who actually go to like international mathematics Olympics and so on, and then I have some advanced course where basically we always give tasks to do and everyone on site. So but we could try to do this, but then it takes not 2 hours but like 4 or 5 hours. So the coder. So but I will make a smaller task now. So this is session 9. Okay, cool. Okay, cool. It's 9.2. There should be now the template. I will also. Oh, it's so yeah, but it is available. I will just clean it up a little bit and get it myself. So we need to implement encoder decoder, and the Z shape must be 32 dimensions. Okay, cool. So Z shape 32 dimensions. So this I open. Okay, I see the template. Let's call it live 2024 Q4. Okay, here. You got the template, yeah? Okay, cool. I'm getting there as well. So make sure that this works for you as well. Hello. The copy, yes. Open PyCharm. Have you tried this new the cursor? Do you know cursor? No? You need to know. So basically, again, please don't use cursor for my homework. So, but I mean, just like for learning stuff, this is not optimal. But for making like fast code, this is excellent. So definitely try out. So this is also a language model based IDA. Like so, this is basically you can select piece of code, ask to rewrite it in different way, and like I know people building apps and things like extremely fast with this tool. So I think this is like a future of programming. Kind of the good news is that these AI models, you still need a little bit of brain to make them, but for just making websites, applications, you can imagine how fast you can do with this. Yeah, but definitely worth looking at that. So that's something I use myself with regard. So when I need to develop something, and then the PyCharm is better for debugging right now. So PyCharm, where are you? Why it says on title? Oh no, right. What is this? Small tools? Yeah, no. PyCharm small tools. Okay, cool. I have it. So I think okay. So this will be good. Okay, let's look what's inside there. Again, if you have your own GPU computer, then this is my hack to make sure that I can run something. So if not available, so in case if you have GPU computer, then just do this. but otherwise, this is a hack to debug my code basically. So then apples dataset. Okay, this is I think something different than fruits. I think there's just apples. Oh, I think there was like the Royal Gala, the green apples, and so on. All those apples. So what else? What else? Auto-encoder. Yeah, here. Encoder, decoder. The middle part Z here. By the way, there exists also a reshape. So this function. The rule of thumb how to use reshape or view, you always try to use view, and if you get error, then write reshape. Because what it means is view is just if I have in memory rows one by one, then I can allocate that this is long line. But if for some reason my rows are separated by other memory block, it will not work. It will tell there's an error because they are not continuous. But it's just that rule of thumb. So then view, I think this is a little bit, right. I did the view one by one because I need to make it again larger, no, as an 2D object. So what else? Here I think in the bottom part we have, see the PCA scatter plot, so NPZ dimensions. Where did I get? Okay, so here. So this is cool. See, there is a decomposition PCA2 dimensions. So this is something that you can change and play around. There could be also other decompositions, like for example, the same, there should, okay, I'm not sure why it's not showing me, but there should be TS&E as well and others. But we can leave it as it is. I'm not sure why my autocomplete is not working, whatever. So, okay, so we need to do these parts, decoders and encoder. Okay, and I actually have here some kind of dummy code already for upsampling. If I run this, it will work, but it will not be nice. Okay, let's try it. Let's try. Okay. So I think I have some brief architecture formula, at least how to do this better. Because if I will try to do this from top of my head, then I might miss something. Okay, let's think how would be the easiest way. 721, 721, 721, 721. Kerning, padding, stride. Okay, cool. I got it. So I think that for all of us will be faster if we will just write another block here. So this will be, let's call encoder block, and we always need to call this def init and super init. Even if Python works also with this, if you will not call super init, you will have problems, because super init will look for variables that are in the constructor. And so basically Python is not like C++, Java. It's a functional programming language. You need to call yourself constructor. So that's that. So this will be okay. Let's then call it self layers. I'm just writing right now from top of my head. We'll see if I don't make any mistakes, hopefully. So torch and convolution 2D. And what I like to do is always convolution, then batch norm, then relu. But I know some architectures have this an other way around, but this makes the most sense always. So then the input parameters, actually we need something. So we need in channels, out channels, and kernel size. Yep, and we can use them here, here. Then only I want to make sure that the kernel size, yeah, stride. Let's use also stride. What is the right order? So in channels, out channels, kernel size, stride. Yes, this is the right order. If the order is right, then we can just use it like that. Cool. So what needs to be in the batch norm? Do you know what should be the parameter there? Num features. What should be there? Out channels. Yes, out channels. But the so with the there is actually other norms as well. So we will talk about them later. But there is, you see, layer norm. There is an instance norm. There is a group norm. So all of these have a little bit different way how they normalize. Batch norm normalize by all of the samples in the batches by the out channels dimension. So that's that. Then def forward, again forward self x is the input always. Return, in this case, this is not the buggable code, but there is very little to break something, so I just write like that. Okay, so this is my encoder block, and then I will use the encoder block a couple of times to squish my data, basically. So in channels, the RGB image, my fruits, then out channels. I will make the out channels larger. Try to make it the power of 2. Power of 2 is always optimal for calculations. Then stride 1. First kernels are usually a little bit larger. So then stride 2 means reduce 2 times most cases. So then what else? Oh, so I forgot about padding here. Okay, let's add, so there is a pad, what is the default padding? Okay, yeah, the default padding is 0, so padding 1. Okay, let's do that. Up here, padding 1, please add there padding 1. Okay, cool, stride encoder, right, that will be good. So they're from 4 to 8. From 8 to 16, let's do 8, 16. What the kernel size? So these parameters are just like they are found to work for this case. You can use any other parameters, but then you make sure that the middle part is the right size, 32. So it's we could actually use the adaptive average pooling. Anything you use there will work, so it's quite actually open to change the other way as you like this architecture, so it doesn't need to be the way I write it. 5, 2, just make sure that the output is 32. So 5, 5, 5, 5. So there's a stride 2, stride 1, so it's a little bit maybe too complicated. 1 2 1 2 1 1 2 again. If something will not work, I will just use adaptive average pooling, then everything works. So 32, 32. Okay, and do you remember this thing? Kernel 3 stride 1 padding 1. What will be the input output? Do you remember that? So 3 1 1. Remember? No? So what is interesting about this combination? So it is, if I have an image, let's say 10 by 10, if I use this, then it will be 10 by 10 again out. So this is the typical combination in any AI, these deep learning models, to make sure that the image size don't change. So they always use 3 1 1. So maybe you can find other combinations as well, but this is what they always use. So 3 1 1. 3 1 1 1. Okay, cool. By the way, okay, cool. Well, let's leave it. So and then yeah, just to make sure that I didn't mess up something, let's add the adaptive average pooling. Adaptive average pooling out size 1 by 1. So if I would no, but this is, yeah, so this is the compressing. So if I would compress it too much, so it means that if, for example, my image becomes less than 1 by 1, then there will be error, and then we just delete a couple of things, but otherwise it should work. So this is one way of doing it. It's not the only way. So you can make your own architecture, just make sure that it's compressed to 32 by 32. So I will now put this on the whiteboard, try to run it, and then we'll look at some other things. So run. How do I? It's computer a little bit slow. Oh, what is that? That's interesting. That is very okay. Loss function not implemented, right? So I think everyone can implement this one. Oh, there's also interesting thing. So this is something to notice. See, I returned two variables here, but just for you to remember, I told you this in the very beginning. So it's not actually returning two variables. It's returning one variable. Do you know what is the variable type? What it's returning? It's returning tuple. So like basically this means this, and it's like Python is, if you read it, you think, okay, two variables, actually one variable, but still you can decode tuples into multiple variables. So for example, if I go down here, so here I assigned this and this. I can actually also do this. Usually in Python, if you don't care about some variable, you do that, the underscore. So what else? So the tuples actually can allow you to do something crazy as this. For example, I think in the very beginning I showed you this, right? So I can replace variables in Python like that. So without, so and here I just wanted to highlight this because your model now returns not only the predicted image but also the z, and that z is actually in many cases the product that you actually want. This is the middle vector. So and here the loss function. So the loss function, I think we can choose. I like better the L1. L1 is more stable than L2 for any real life data. For basically, so let's use the L1. So mean torch ABS y prime minus y. There's y target, right? Okay, cool. Oh, there's also label here, but label we don't use it. It's just for visualization. Okay, so cool. I'm adding that, and then try to run it. And you also try to run it, and if bugs will help. And, okay. run. Okay, now it's training. It will definitely need to run this on Google Colab, because now I have just a few samples here. So this is not, so this, okay, so there's multiple things going on. So first thing is I have this limitation of training just for debugging. The other thing is, see, I have those red apples, but then for the upsampling, I just have this is nearest sample upsample to 100, and the convolution. By the way, this also is really cool. Maybe we'll talk about this a little bit later, but basically this is not, I think this is not derivable function, or maybe it is. Let's see. Nearest sample, like here it is. So I think this is one of those functions where the derivative is not exact solution. So you could actually, sometimes in these models, you can put inside, let's say, bilinear upscaling and things like that. See, bilinear, which might not be easily derivable, but if you have some approximate derivation, it also works. Or even sometimes you can skip for quantized autoencoders, you actually do that. So okay, so this is that. Did you manage to do these red blocks? Worked for you? Works? No.
My computer crashed.
Oh. Okay, it's not great.
It was a long day.
Okay, yeah, me too. Very long day, but okay. So yeah, but then you need to find the time to work on this a little bit. Okay, so I will maybe use this on this one. To jest monta, vai ne?
Jā.
Tev iet, vai? Okay. Okay, cool. So, collab. Un atgādini, kā tevi sauc? Aneta. Okay. Forši, tu esi no maģistriem vai no kaut kuriem citur? Mhm. Tu iepriekš arī biji no robotiem vai no kaut kā cita? Wow, tev noteikti baigais izmaiņa, ne? Pēc tam mēs varam par to parunāt. Ok, tā, rekur run, tā, vajag uztaisīt. Kā viņš viņu visu laiku pārslēdzās uz latviešu valodu, vienkārši šausmas. Labi, izpildu laiks, mainīt izpildu laika veidu, GPU. Es vienkārši gribu viņam kaut ko tu palaist, run. Labi, lai viņš tur iet. Vai es labi sapratu, ka jūs arī noguši, tas nemēģināšu varbūt, es vienkārši mums kaut kas šis jāiziet cauri, bet kāds daļas varbūt izlaidīs. Tā, labi. Ok, tas ir encoders, tagad tas decoders jāuztājas, so the decoder must be built. So here, right. Again, so those transposed convolutions, basically, transposed convolutions are already available in the PyTorch. So again, I will just copy this block, encoder block, and make a decoder block. If everything goes right, we will have nice visualizations. Decoder block. Here we'll use conv transpose 2D. Okay, that's that. And otherwise, I think it's the same actually. So yeah, so not just one change. One change. Also, there we need. Okay. Yeah, let's do that. Will work. Okay, I will put this on the whiteboard. We'll also maybe look at the comments on the YouTube. Maybe there's any comments, questions. Right. So I have 2 likes, maybe from you. Anyway, so, yeah, I remember, so there are a couple of other students, and you see in the homeworks there people are actually doing things, so it's not really that bad, but for some reason people are not wanting to come in person, and it's kind of interesting because like I think if we talk on the person we can fix things better. So okay, let's see, decoder block, yes. So in channels 32 dimensions, out channels. I forgot to mention that the z vector dimensions, you might think that, let's say, if I build model with 120, I don't know, 4, whatever dimensions, it will be better, but actually it's not the case. There is the course of dimensionality. If you have more dimensions than usually about like 128, 512, then all of your vectors, like in the space, the distance, like the cosine angle between them becomes almost zero, basically. So basically, the more dimensions you have, at one point it becomes actually z vectors become worse. So this is kind of also interesting thing. Okay, so in channels 32, kernel size 3, stride 1, padding 1. Oh, shit, padding. Okay, padding I already have there. Okay, cool. So this will be the next one. 32 to 16, 5, and 2. The 2 actually this time will make larger the image. So then 16 to 16, 5, 1. I think it will be 1, 2 all the time. So then 16 to 8. Yeah, 16 to 8. 16 to 8, 1. Right. Oh, there is one more of these guys. 16 to 16. 5 to 1. 5, 1. 5, 1. Okay, let's then try to collapse it quickly. So 8 to 4. 8 to 4. To 2. No, 7. Let's say 7 larger. 2. And then 4 to 3. RGB. And by the way, here again, if you follow a little bit here, what we could do, we could have num classes. Don't write it like that, but we could make it that this model predicts masks, for example, right? Each channel is different mask, so this is how it actually works for some semantic segmentation. So kernel 8, no, let's see, yeah, 8, 1. And then again, I'm not totally sure that my sizing is correct, so I will just add adaptive one here. This is definitely not for the best results, but it will be at least some result. So 32. Okay, cool. Okay, so if I run this here and then I will run it on Google Colab, hopefully it will work. Jigs, stop. It works. Run. Oh, what is that? Okay, this is interesting. Output size, it should, oh no, not 32, right? This is my mistake. It must be 100. Okay, the fruits are a little bit larger. So run. Okay. Okay, now it works. Good. Oh, it actually gives me these interesting patterns. Okay, let's see how this works on the Colab. Oh, we also starts working really nicely. Okay, by the way, the output is not that great, but the Z it actually looks really nice. So okay. Yeah, but it's not now even becoming something visible here also as in the output. So in the output, at least it starts to become similar to the green apples, red apples, and so on. And in the Z vector, so the cool thing is in the test space, these are not the samples that were in the train space, and they still cluster in those areas. We could actually, it would be even better if I take some class out and just leave it in the test space. then it would look even more interesting. Okay, the decoder part is not great, so my hacks are probably not the best ones, but there is something interesting there. I will show you. So okay, so these we already see this, that there is this checkerboard artifacts. So these checkerboard artifacts is actually something common with transposed convolutions. For transposed convolutions, this is this is something that happens often. So what usually people do, they add also these upsampling, bilinear upsampling, and things like that. So let's see if I can find some better example of that. Okay, I'll put in the Jamboard a couple of things. So because of saving time, probably we'll just leave example for that. So this we had the decoder block. This is the decoder, cool. And then how to make it look a little bit better. The modern duration autoencoder. Let me show you how to make it a little bit better. Okay, I will then open another task later, but basically the one way how to make these architectures look a little bit better. So this one is copied from NVIDIA paper, one of the papers so some time ago already, but the DAE still holds. So you could use so regarding the group norm, let's talk about group norm some other time. But basically, it can be batch norm, and this can be ReLU. The mesh function is just similar to the ReLU, just even similar to the leaky ReLU, but without any hacks. So, but here there is this. So this doesn't look really right, so I don't like it. I know that there is upsampling even better ways. Well, let me see. I have seen better implementation. Okay, this one maybe is a little bit cleaner. Okay, let's use this one. So, okay, I like this one much better. Okay, let's show you this one. To avoid these artifacts, and I will just copy this and try to run again that experiment to just prove you. So what you can do, you can use bilinear upscaling and then use convolutions with this 311, so it learns how to basically improve quality. So it's basically really like upscale, improve quality, upscale, improve quality, upscale, improve quality. And actually this kind of architecture works better for decoders. So I'll just copy my decoder architecture and then try again. Also, I just realized maybe I made one mistake. Yeah, probably. So I will show you the mistake. So far, these fruits try to get the result. Oh, but it's actually not that bad. See, it's already becoming. Oh, I know what's happening. So see those huge black spots, and see also here it says that RGB must be from 1 to 0, right? So I forgot to limit the outputs. So now it is like basically above that range, and then it becomes really strange, these artifacts. So what do you think, how we can limit output? Do you have ideas? Like to avoid that we have any arbitrary output range here. So I can give you a hint. So if I go to the architecture, and all of these things. So if I go to the decode, it must be change in decoder. So see the decoder. Remember the another hint. Remember that we have the classification task, for example, and we don't want to give each class probability from minus infinity to plus infinity. Then what we do? We add softmax, right? So, and here to limit everything between 0 and 1, yeah, sigmoid. So we can add here torch and if you do this, then it will look much better. So but that's one. But then also I will just copy my this part. So if you add at the end torch and then sigmoid, it will definitely be better. And this is not the only function. You could use other ways if you like, but this is something that is important. So sigmoids, by the way, also are used if you have a situation where each class is independent of other class, and then you could train it with KL divergence. We actually will talk about KL divergence probably today a little bit. So okay, that's that. Let me run it. So stop it. Stop. Oh man, it's not stopping. Restartēt izpildu laiku atcelt. Okay. Hopefully it will stop, then I will run it again. Meanwhile, let's go on. So this is so far the autoencoder, but then there are a couple of updates to the autoencoder. So update number 1, where is the update number 1? That's really simple. So the update number 1, which for some, it might be interesting to find the reason why it actually is the case. I could ask ChatGPT or Perplexity and try to understand the kind of reasoning for this, but this is the case. So if you have, if this is called denoising autoencoder, denoising autoencoder. So the idea is that your inputs now are deliberately damaged, basically, right? You just I'll put that randomly every third pixel becomes 0, for example, inputs, but the outputs are not damaged, see? And if you do that, it suddenly the Z becomes better quality, basically. So these are called denoising autoencoders. The reason why it works, I'm not totally sure. I need to look up if somebody has proven why it works better. But basically, that's one of the common ways how to do. So to add noise on here and then here the results. Maybe it works because if I use the new classes, novel classes that have never been seen, then it might learn too much existing shapes. If they are damaged, then maybe it is more flexible to new shapes, for example. So I will later open the task for this. This is really easy to change from previous one. So this is one, but I don't want to stop here. So that is the denoising autoencoder. And then the next update, which is way cooler, and maybe I'll try to, we'll definitely need to try to give you the guidance how to implement it a little bit, because this is significantly really good, really proper interesting model. So these are the variational autoencoders, variational autoencoders, and these start to become really interesting. So do I have a loss function somewhere? I just want to find, because the loss function will be built from multiple parts actually. So this will not be just one loss function. So let me show you. Have any of you ever seen KL divergence, things like that? No? So this is from probability theory. So and this is like a measurement, you know, like a Euclidean distance, like a cosine distance, but for the probability distribution. So and the loss function at the end, so we will unpack this step by step. It is not also that complicated, but this is really cool. So the loss function actually now consists of reconstruction loss and the KL loss here. And the KL also have this beta argument, the hyperparameter, which pushes the importance of this thing more or less. And for the KL divergence, we have the standard deviation, and we have mean here. And we get or maybe I should color these things so you know where they are. So standard deviation comes from, so where it is, actually, yeah, so this thing, so this is standard deviation. And the mean is this thing here, right? And the output is here, and the output is here, okay? There's also here another standard deviation, that's the same one. So that's that. Then what's happening here and why this is really cool. So this model now produces not just z, it does not produce at all z vector. It produces two vectors, mean and standard deviation vectors. Both of those vectors are 32. So this is like batch comma, right, batch comma 32, batch comma 30. And the other one is also batch comma 32. Then to calculate z vector, we actually use this part, so basically here, and then after calculating the z vector, which is this one, we will plug it in here and run it as a normal decoder. But here, so this is really interesting. So here, what's happening? So the orange mean vector, then the red standard deviation vector. Then this means just a pairwise multiplication, Hammond product, and this epsilon is not the error, but this is the sampled normal distribution sample. Also, this, by the way, is B32 size. So just from random distribution. So and what's happening there is that we are simulating the probability distribution using constant of this this normal distribution, and actually I can explain what is the difference, why we need that, but let me show you more, a couple of things. So I had this diagram of where the error goes. Okay, so this diagram. Okay, cool. Is it the whole diagram? Okay, we'll just make the part. We'll show you in a second also that the results of this. So so here, this kind of model is really interesting, because now we have instead of just getting the gradient, so there is a so where it is, so this is the output. Then we have z vector, and we calculated the z vector from these two nodes, but this node is just like a constant, but that constant changes every time I run it. So this is really interesting. Like normally you could have one constant that is fixed, but now this is changing, and this is changing by the normal distribution, right? Like from the normal distribution, sampling anything from there. So that's that. Why we actually doing all of this is that for this KL divergence, the idea is that we are measuring how much your probability distribution, all of the possible cases when you ask to generate from your function samples are how far it is away. So for example, here is a visualization. So there are KL divergences. So like it depends on which order you put it in the function. So but basically, if you see here, so let's see. So there is the KL is small. Okay, actually I like this one better. So here the blue one is my prior, and green one is posterior. So I want to make sure that that my green one is as much as aligned with the blue one. And here on this case, this is large because it is not fitting. The average error is very far. So that really doesn't matter, even if it's this or that. but basically the idea is that I want to make sure that my distribution of green one is very similar to the blue one, okay? And this KL is the number, just one scalar number that tells me how far all of my distribution is from the other one. And the reason why I'm trying to do all of this is to make sure that basically my z vector is not just one number, but I have this thing, and then I can, in production, I can sample things. I can make it really generative model where I can just run it 10 times and I will have completely 10 different images. There is actually really cool things going on there, but I'm just starting to feel that maybe it's too late and too much today. So okay, I'll just let's leave it as that. That you know, like you can think about it, and then we'll continue next time. But I just want to add one more thing here, because this model is really unique, and we did not touch the main thing. So the main thing is this one. So the loss functions, when we will try to do this, will go like this. It looks chaotic, but it's actually what we want to achieve. So why it is that? So there is the let me color a little bit. Reconstruction loss. Where is the? So this is reconstruction loss, and this is train KL loss. So what is this? Okay, so cool. So the KL goes down, and then it starts to go up, and then it starts to go down again. You see? And this is actually what you want. Also, when you look at generative models GANs, later you also see something as crazy as that. The reconstruction loss goes down all the time. That's good, but the KL should work like that. And why? This, I think, hopefully I have the image here, but this is really cool. So initially, all of your images will look like this, basically. So they will look all of the same, and later they will start to resemble the actual pictures. And why is that the case? So here I have actually one visualization. So what it happens is that there is this Z space, so I need to be careful to look at this diagram so I don't mess up. So here is the original image, reconstruction image, and then these things are meant to be, I believe these things are meant to be the Z vector. So this is a 6-dimensional Z vector, and then what it meant by these things is just like if I change the values in that dimension, how the output looks like. And what is really cool about this, if I have this beta 1, the small beta, or no KL at all, if I would have no KL at all, then in all of dimensions I would have something there. As soon as I have larger beta, what happens is that I am forcing my Z vector to become normal distribution. So, and if my Z vector is normal distribution, then basically what happens is then I stay like this forever. So basically no use of that. But if I force it out, at some moment it breaks, and what happens is this, that it automatically, without any intelligence from the creator here, creates that, okay, I have an image where there is a ball bouncing on Y and X. So I just need 2 dimensions. I don't need all of these other dimensions. I don't use them. Basically, all of those dimensions are perfect Gaussian distribution. And so if you can kind of catch it, what I'm saying here, it's like really extremely cool stuff. So basically, just by forcing this KL equation to this Z, it suddenly, in the very beginning, acts against you. It says, it tries to make that, so the KL loss goes down, so it makes that all of your pictures looks like this, and then at some moment it starts to go up and optimizes itself how many dimensions I need. So this is like really cool, and if you do this, then all of your Z space actually is really smooth. So with other methods you get this kind of Z space where it's suddenly I have like the cats, dogs, cars, and so on. But with this one, you would have like cats, dogs, lions, and then somewhere along the way there is a car. So you get it, right? So and then just need to make sure work in the code and mathematics, and but it's also not that difficult. It just need a little bit of attention there. So okay, let's look at that next week, and then I will. So next week then will be a little bit of mix of this, and then with the time series probably. But let's look at what I have. I need to actually calculate how much we can manage till the new year on deep learning. Oh no, I thought the next week I would try the UNet segmentation. So then this goes good together because I can show this and then immediately I can show the segmentation. Okay, great. So that's it for today. Online people also let me know if any questions, and let's meet you next week. I will update where and what time. Okay, bye bye.